So first sense, or first taste of the inharmonicity you can get, even is still staying in a harmonic part of your physics by just looking at the Gunaisen parameter. Is essentially the logarithmic derivative of your phonon frequencies with respect to volume. And if you, so again, I'm not going to tell you to go on and do very involved thermal conductivity calculation, but just look at the Gunaisen parameters and see how that looks like, and what you will, and thermal conductivity is inversely proportional to Gunaisen parameter. So here we have plotted all the Gunaisen parameter, and you could see that the order which you see here, which we get for the Gunaisen parameter, is exactly reverse of the kappa L, which is what was expected. So if a high Gunaisen parameter is what we need, and this material gives us a pretty high Gunaisen parameter. So, but we did not stop here. We went ahead and calculated the 3 phonon phase space, 3 phonon scattering phase spaces here, and which comes out to be very similar what was predicted by Gunaisen parameter. And therefore, we finally able to get the material which turns out to have a ZT of the order of 1.8 for the p-type and around 1.9 for the n-type material. And if you put it in a perspective, this lies in the range of some of the best known thermoelectric materials, which are even experimentally as well as theoretically predicted, except of course tin selenide and lead telluride. So here is a conclusion of the first part, but I will not read through it. Rather, I will go to the second part of my story, which is breaking the inverse coupled dependence of S and sigma. So as I showed you, for metals, sigma is very high, but S is very low. And for the insulator, S is very high and sigma is very low. So they have an inverse coupled relationship. So is there a way to break it? Of course, there is a physics why it behaves like that, but sometimes it's good to challenge ourselves and see why, how to do that. So this is the material which we picked up, Bi2S3, because this belongs to the same class which produces a very high ZT thermoelectric material, which is bismuth selenide. And but Bi2S3 is not a good thermoelectric material. And if you look at the literature, the maximum ZT which you get, and that also depends on the processing and different experimental results, up to, let's say, 0.6. That's it, not beyond that. If you believe that experiment, but most of them lie somewhere around 0.35, which is a very low ZT. So the question is how to get, at the same time, bismuth telluride, which has a ZT of 1.3 in the same family. Of course, this is well understood why it has. So the idea is bismuth sulfide is going to be much cheaper than telluride. Telluride has a rare earth, whereas sulfur is everywhere. So it has a cost benefit also if we can do that. So how do we do that? So we'll have to look at the reason, or a little bit deeply, what is the exact dependence of S and sigma. So if you look at that, the sigma depends on the conductivity effective mass, M star, inversely proportional to conductivity effective mass, whereas S is directly proportional to density of a state effective mass. So if you want to increase the S, at the same time increase the sigma also, you need to lower the conductivity effective mass, and you have to increase the density of state effective mass. And this, can you do this simultaneously? That's the idea. And if you take a parameter like R and try to plot m DOS over m cont, which this ratio we have to increase, because, and if we get this, which is essentially m in the perpendicular direction and in the parallel direction, then you can get, for let's say somewhere between 0.01 and 0.1, a pretty high number of this. And if that can happen, things will become very, very interesting. So what do I mean by that? So here is the usual picture which you will get it in any semiconductor which you pick up. However, if we get, so this is a wishful thinking, if our M conductivity somehow decreases and M DOS is somehow increases by some perturbation, and here I'm showing you is the pressure. So if you subject it to hydrostatic pressure, we always know one of the other reasons, bismuth sulfide has a large band gap. Not large, but good enough band gap. So when you subject something to the hydrostatic pressure, usually band gap decreases. I will tell you why, but if time permits, but let's focus on how it changes the effective mass. And we do a lot of work on the pressure-induced phenomenon, so this idea we picked from there. How about we subject it to the pressure and see if that can happen? But what we actually wanted to achieve is not the reduction in gap, but somehow if M conductivity can go down and M DOS can go down, if that is the case, then we will be able to break the inverse coupled relationship which I showed you, which is this picture, right? So this is a very ambitious thing, but yeah, we would like to do something like that. So here is the electronic structure. I will not waste too much of your time, and you see when you increase the pressure, what happens, you know, it's like you can understand in terms of LSCO, when you're bringing the two orbitals closer, of course, their splitting will increase, but the bandwidth also increases simultaneously. And if increase in bandwidth is more faster than the increase, they're splitting, then they come and they overlap and they become metal. So this is what happens here, but that part is probably not interesting for this particular study. What is interesting for us is this part, how the effective masses changes. So we could see that. So this is the conductivity effective mass, again, for the P-type and N-type. And we see for some of the cases it is increasing. For example, here, up to 6 gigapascal on an average, there was some increase. Sorry. And this was the density of state effective mass. Sorry, it is decreasing. I'm really sorry, because you see. And density of state effective mass is the one which increases on an average. And this is what we wanted, up to 6 gigapascal. So if you combine these two, what do you get? Here are your S and sigma. Sigma is on this axis and S is on this axis. And you see up to 6 gigapascal, S is increasing, as well as your corresponding sigma is also increasing. So everywhere you see. And that is a very, very interesting result. And if you combine these two, the power factor goes up and increases by almost five times what you get at the zero pressure, and it reaches some very, very high, up to 6 gigapascal. Of course, after that, the usual physics takes over and everything falls down, which you see this part. But up to 6 gigapascal, you would be able to, or at least we have shown, that you can break the inverse coupled relationship, which I have shown before. So, yes, okay. Yeah, so then I have to finish only with this story. That's okay. So that part is done, but you know, as you also know, if you subject something to the pressure, you are hardening the bond length, right? And that means the thermal conductivity can increase. It's not always it softens. Sometimes, at least for the low pressure range, it actually hardens the phonons. And so we have to check. If that is what is happening, that means phonon group velocities will increase, and our thermal conductivity is also going to increase. And if that will happen, then whatever gain which we are getting from the electronic transport will be compensated by this part. So we have to look at that if that is happening. So we checked it, and in fact there is something even worse happens. There is a phononic gap which comes out at the 6 gigapascal. It's an interesting thing, but not for us, because if you have a phononic gap, that means your thermal conductivity is going to be further increased. So these things were not very encouraging, but we looked at it, and what we found that with pressure, indeed the thermal conductivity went up, as you can see, but up to 6 gigapascal, which was what was our interest of the pressure range was, the increase was not that much. So somehow we were fortunate to not get the very strong increase in lattice part of thermal conductivity. It actually remained almost more or less same. So up to green curve, you should pay attention. But of course, as you see at 13 gigapascal, it went very high. So this was the range which we were concerned about, and the thermal conductivity was more or less remained same. So we have gained almost 5 times or 4 times in power factor, whereas the gain in thermal conductivity was much less. And if we combine this all together, we get the ZT of the order of almost 1.2. So we started with a material which has a ZT of 0.3, less than 0.3, and we can go all the way up to 1.2, which is by breaking this inverse coupled relationship. But now the question is not, many of you here, we have several experimental talks, right? Nobody likes to do a thermoelectric measurements done under pressure. That would be a very expensive system. So as an idea, it was very good, but not as a practical system. So we looked at the literature of superconductivity, where there is the idea of a chemical pressure. So what you can do, you can dope with the isoelectronic element, either of the larger size or a smaller size, and you can effectively generate some kind of a chemical pressure, which is equivalent to what you have applied through the hydrostatic pressure. So this is what we did, and we found, without going into too much details, the effect which you get by applying the explicit hydrostatic pressure, you can reproduce the same thing by just up, but the range, we could not go up to 6 gigapascal, but we stayed, let's say, up to 2 or 3 gigapascal, and But we got one added advantage. Since we have doped, we have created some kind of a mass imbalance. Therefore, the thermal conductivity got a little bit lower, and we maintain again quite high ZT. So this design or this rationale which we came up, of course, this was completely our idea. This was not there in community, and with which you can improve the ZT of a thermoelectric material by several, at least a few couple of times. And the last part is engineering the defect transition levels. I can quickly tell you the broad idea of what it is behind. As you see, most of the time the ZT peaks at a particular temperature, right? So suppose you have an application where your temperature difference or the which you are looking for is just 500 degree Kelvin, or you have another application where you need 1200 degree Kelvin, but the material is which is given to you, its ZT peaks at, let's say, 800 degree Kelvin. So and from 800 to 500, the ZT falls like anything. So it's not going to be useful material for you. So the question is, how do you change or how do you tune where your ZT peaks? Okay, so this was not an unanswered question in the literature. Even now, I think we have tried something, but it requires much more work. So essentially what we showed, this is a chromium disulfide was our toy system. We worked on it, and we found that if you put the defects, and as you know, when you dope something, defects create a defect state, right? Defect transition level. So for the value of a Fermi level or chemical potential at which the defect changes its charge state from, let's say, neutral to negative for a acceptor, and so the position of these defect level for both acceptors and donors, which you have seen in your textbook also. So this is the defect transition level. This is a thermodynamic defect transition level, and this is the position of this guy tells you if something is a shallow or deep, right? And if you convert the position of this DLT to a temperature, corresponding temperature, and calculate your thermopower, you will find, or what we have found, is essentially one-to-one relationship, a linear relationship. So if you can dope your material with a defect, which can give you a defect transition level, whose temperature value is at what your is equal to the application where you want to run your machine, you can tune your ZT to that value. And this was what we did and showed. Of course, I don't have time to go into the details, but if you have questions, we can discuss. And here are some of the future search for thermoelectric material. Nowadays, everything is going through high throughput material search, where at the same time you have to filter out a lot of materials, where we have started using the machine learning techniques to filter out, as well as discovery to accelerate the discovery of newer materials. So this is the direction in which now currently people are going in terms of the search for the material. But still, these let's say checkpoints, what are the things which we should look for, even if you like to filter it out? What are the good markers which can tell you that whether it's a good thermoelectric material or not, remains an important area of research, where I have shown you at least 3 pointers, and maybe we'll find a couple of more, which I can tell you some other time. With this, I will stop here. Thank you very much for your attention.